Good morning, students. I am Vishnu Prasad here. So I am going to teach the applied thermodynamics. Already we have finished the class 1 and class 2. So in the class 1 I have explained you about the single stage reciprocating air compressor with clearance and without clearance. So in the second class I have explained some problems. So in the third class I have explained you about the multi-stage air compressor. There is a two-stage air compressor and more than two stages also. So what is the work done, work required per cycle to compress the air? We have derived the formula. Okay. So based on this multi-stage air compressor, now we are going to solve some problems. So this is the first problem here. So it has given that in a two-stage compressor, the work required is 350 kilojoules per kg of air. It is used to compress 1 kg of free air from the atmospheric pressure of 1 bar and 32 degrees centigrade. If n value is equal to 1.3 and R is equal to 0.287 kilojoules per kg. So is asking to find the intermediate pressure. Okay. So we first required to find out the intermediate pressure. Before to that, we should know whether it is single stage or multi-stage. So it has given clearly that it is a two-stage compressor. So applying the formula, that we know that work required for a two-stage compressor is given by 2n by n minus 1 mRT1 into P3 by P1 to the power of n minus 1 by 2n minus 1. So we have taken the 2n indicates it is a two-stage compressor. So to find out the intermediate pressure, we should find out what is the suction pressure and the delivery pressure. So in this problem, he has given only the suction pressure and also work done he has given. So by substituting here, we are going to calculate the P3 value. So when you substitute and find out the P3, you will get P3 equal to 26.78 bar. So already we have derived the intermediate pressure or optimum pressure. P2 is equal to Pi is nothing but square root of P1 and P3, that is suction pressure and delivery pressure. So suction pressure is given as 1 bar and delivery pressure P3 we have found out applying the work done formula, it is 26.78 bar. So square root of that we are going to get the 5.17 bar. Okay, so this is a basic simple problem. So in the next problem, he has given the determine the minimum work required to compress 1 kg of air from 1 bar and 27 degrees centigrade to a pressure of 9 bar in two stages. The law of compression is PV to the power of 1.35 equal to constant, and for perfect intercooling. Okay, he is asking what is the percentage of saving in work by compressing in two stages. So in this problem, we are supposed to find out the work required to compress the air in single stage and what is the work required to compress the air in two stages with the perfect intercooling, is saying. So if you find out the work done separately, then we can find out what is the saving of work by compressing in two stages. So if you look into the diagram here, 1 to 4 compression takes place in the LP cylinder, 4 to 2 cooling takes place, and 2 to 3 compression takes place in the HP cylinder. So here initial pressure, atmospheric pressure he has given P1 is equal to 16 bar and initial temperature he has given T1 equal to 27 degrees centigrade, and the delivery pressure, that is P5 is also equivalent to P3, that is also equivalent to P6, that is nothing but the delivery pressure after compression in the HP cylinder. He has given it as 9 bar. Okay, and he has given the n value as 1.35. So we know that for work required for two stages by perfect cooling, it is given by work done is given by 2n by n minus 1 m P1 V1, or it can also be written as mr T1 in the bracket PD by P1. PD indicates the delivery pressure, that is P3. Okay, PD by P1 to the power of n minus 1 by 2n minus 1. So substituting all the values here we don't know the volume, actual volume of air intaken, but he has given the initial temperature. So instead of P1 V1, write it as mr T1. So substituting all the values, you will get work required for two-stage air compressor with perfect intercooling. By applying the formula, you will get 218.87 kilojoules per kg. So now we will calculate separately the air required for single stage. So for single stage, we know that n by n minus 1 mRT1 into delivery pressure by suction pressure to the power of n minus 1 by n minus 1. So from this we are going to get, instead of placing 2n, you are writing just a n here because we are considering it as single stage. So P1 is the suction pressure and P5 is the delivery pressure. Okay, so substituting this, we are going to get the work done as 254.936 kilojoules per kg. From this, we came to know that work required by compressing the air, for compressing the air in two stages is less compared to compressing in a single stage. So by two stages, we got 218.87 kilojoules per kg, whereas by compressing it in a single stage, we got work required is 254.936 kilojoules per kg. So the percentage of saving the work is nothing but 254.93 minus 218.87 divided by 254.93. So you are going to save 14% of work required to compress the air when it is compressed in a two stages. Okay, so the next problem is a two-stage air compressor delivers 1 meter cube of air. So he has given the volume of the air delivered, it is 1 meter cube of air per minute at a pressure of 14 bar, means delivery pressure he has given as 14 bar. The suction pressure and temperature he has given as 1 bar and 20 degrees centigrade, and the index of compression is 1.25. So for both the stages, the intermediate pressure is optimum, is saying. So when it is optimum, is nothing but square root of suction pressure and delivery pressure. So he is asking to find out the power required for compression and heat carried away by the intercooler. Means what is the amount of heat that is taken away during the process from 4 to 2. 4 to 2 is nothing but your intercooler. So first we are going to find out what is the intermediate pressure. Okay, so intermediate pressure is nothing but square root of 1 into 14, it is 3.74 bar. So first bit he has asked to find out power required for the compression. Since it is a two stage, so for two stage the work done formula is given by 2n by n minus 1 P1 V1 PD by P1, nothing but delivery pressure by suction pressure to the power of n minus 1 by 2n minus 1. So substituting all the values, and if you divide that volume in meter cube per minute divided by 60, you will get the answer in kilowatts. So we are going to get it as 5.03 kilowatts. Okay, so now the heat transferred, the second bit is asking to find out what is the amount of heat carried away by the intercooler. So heat carried away by the intercooler is given by Q is equal to mCp delta T. So delta T is nothing but T4 minus T2. So he has given the optimum pressure, means the for optimum pressure is nothing but for perfect intercooling, T2 will be equivalent to T1 because 4 to 2 cooling takes place. So after cooling, the temperature will be brought back to the initial temperature, that is at the suction condition T1. So therefore T2 will be equivalent to T1. So now Cp is nothing but specific heat. For air we can take it as 1.005. Okay, so now we have to calculate what is the amount of T4. So for the process 1 to 4, we know that T4 by T1 is equal to P4 by P1 to the power of n minus 1 by n. So by this we will get temperature T4 after compression in the LP cylinder. It is 381 degree Kelvin. So now we have to calculate the mass value. So he has given the volume flow rate of the air. Now we have to calculate the mass flow rate of the air. So it is given by m is equal to P1 V1 by RT1. So by substituting this, we will get 1.19 kg per minute. So now if you put that Q is equal to mCp delta T, m is 1.19 divided by 60 to convert into kg per second, Cp is 1.005, and T4 we have found out T1 he has given, T1 is equal to T2. So substituting this, we will get 1.75 kilowatts. So much amount of heat will be carried away during the intercooler. So that's about the problem. So next we will go for the next problem. It is an important problem here. A trial of two-stage single acting reciprocating compressor gave the following data is given. Free air delivery is given. Free air delivery is nothing but V1, that is the amount of air that is sucked into the compressor, that is equal to VA. He has given it as 6 meter cube per minute, and he has given the atmospheric pressure and temperature are 1 bar and 27 degrees centigrade, and delivery pressure he has given as 40 bar. The speed of the compressor he has given, and intermediate pressure also he has given. In this case it is 6 bar. Temperature at the inlet of second stage means T2 he has given, it is 27 degrees centigrade. Okay, it is almost equivalent to the suction condition temperature. And the law of compression he has given, so PV to the power of 1.3 equal to constant, that is n value is 1.3. In this problem he has given the mechanical efficiency, it is 80%, and he has also mentioned that stroke of LP cylinder is equal to stroke of HP cylinder. So L suffix HP is nothing but stroke of HP cylinder is equal to stroke of LP cylinder, that is equal to dia of the LP cylinder he has given. Okay, so he is asking to calculate the cylinder diameter, means you have to calculate the stroke length of each cylinder and also the bore, and also he is asking to find out the power required to drive the compressor by neglecting the clearance. So let us assume that volumetric efficiency as 100% initially. So when volumetric efficiency is 100%, we will get axial volume VA, nothing but, if you look into the PV diagram, VA is nothing but V1. That is also equivalent to stroke volume. That is when the piston moves from A to 1, that is nothing but the stroke. We are going to take the air inside. So V1 is equal to VA is equal to Vs. Let us assume that. So Vs, we know that for since it is 1478 is the LP cylinder, and 23672 is the HP cylinder. Okay. So with respect to the LP cylinder, Vs is equal to pi by 4 d suffix LP square into L suffix LP into N, that gives the total swept volume on the LP cylinder. So swept volume, we know that it is 6 meter cube per minute he has given. So 6 is equal to pi by 4. He has given that bore is equal to stroke in the LP cylinder. So we will get a d cube into 400. So from this we are going to get d value, that is the dia of LP cylinder, is equal to stroke length of the LP cylinder is equal to stroke length of the HP cylinder. It is 0.267 meters. Now the question is to find the dia of the HP cylinder. Okay, so if you look into the PV diagram, the process that is taking place from 1 to 2 is nothing but isothermal process. That is, for isothermal process, PV equal to constant. So P1 V1 will be equivalent to P2 V2. So P1 he has given initial pressure, it is 1 bar, and V1 he has given 6 meter cube per minute, and P2 intermediate pressure he has given, it is 6 bar, and volume V2 is only the unknown term. So from this you will get V2 is equal to 1 meter cube per minute, that is nothing but swept volume of the HP cylinder. So from this we are going to get Vs is equal to pi by 4 d square L into N for the HP cylinder. So substitute the L of the HP cylinder, Vs we have found out it cube per minute. The only term unknown term here is dia of the HP cylinder. So from this you will get dia of the HP cylinder as 0.109 meter. Okay, so we got the stroke as well as the bore of both the cylinders. Now the second bit he has asked to calculate the power required to compress. So we know that power formula is given by 2n by n minus 1 P1 V1, and in the bracket delivery pressure by suction pressure to the power of n minus 1 by 2n minus 1. So substituting all the values, and if you substitute V1 in terms of meter cube per second, you are going to get 45.98 kilowatts. So this is the power required to compress the air. But since he has given the mechanical efficiency, so the actual power required is nothing but power divided by mechanical efficiency. So that is 45.98 divided by 0.8. So we are going to get 57.47 kilowatt. So that is the actual power required to drive the compressor. So this is one of the important problem where we are going to calculate the cylinder dimensions along with the power required to drive the compressor. So that's all for this class. Let us continue in the next